Today it's my fourth video, and today I am going to discuss about the imperfection of solid. In first unit, that is in solid state, the initial part was already covered by the Niranjan sir, and the next part is already covered, that is involving the packing efficiency and two-dimensional packing, three-dimensional packing, and coordination number, radius ratio, etc. was already been covered by Mehra sir. I am going to take up the imperfection in solid, electrical and magnetic properties of solids. So let us learn first the imperfection in solid. In class 11th, in thermodynamics unit, in third law of thermodynamics, what we have learned, that entropy of a perfectly crystalline solid becomes zero at absolute zero. That means at absolute zero, crystals tend to have a perfectly ordered arrangement when their entropy becomes zero, and this arrangement corresponds to a state of lowest energy. What happens when the temperature increases? As the temperature increases, the crystal start deviating from the perfectly ordered arrangement. Any deviation from the perfectly ordered arrangement constitutes a imperfection or a defect. These defects are also called thermodynamic defects because the number of these defects depends on the temperature. Crystals may also possess additional defect due to the presence of impurity known as impurity defect. These imperfections are not only modify the properties like electrical conductivity and mechanical strength, but also gives rise to new properties like color and densities. Thus, the defect which arise due to the irregularity in the arrangement of atom or ion are called atomic imperfections, and the atomic imperfection caused due to the either missing of particles from their normal lattice sites or displacement of particles from their normal lattice site into the void. That is called point defect. Point defect are basically arises because of the two reasons. One, due to the missing of constituent particles from their normal lattice site, or due to the dislocation of constituent particle from their normal lattice sites into the interstitial site known as voids. It may also be caused due to the presence of impurity in the ionic crystals. So the point defects are caused due to the missing of particles or due to the displacement of particles or due to the presence of impurities. Now, after knowing the point defect, we will discuss about the type of point defect. We will know the types of point defect. Point defects are basically three types. Stoichiometric point defect. Second, impurity defect. Third, non-stoichiometric point defect. We will learn these defects in the order of stoichiometric point defect, followed by non-stoichiometric point defect, and at last impurity defect. So let us begin with the stoichiometric point defect. The defect that do not disturb the ratio of number of positive ion and negative ion are called stoichiometric point defect. In NaCa crystal, what we find that there are 6 sodium ions and 6 chloride ion. So the ratio of the cation or positive ion to the negative ion is 1:1, which is identical to the ratio of atoms in their chemical formula, and that is NaCl. Now, this is called a stoichiometric compound in which number of positive ion and number of negative ion always remains same, similar to the chemical formula. Now, what are the stoichiometric point defect? Stoichiometric point defect are of four main types: vacancy defect, interstitial defect, Schottky defect, and Frenkel defect. Vacancy defect and interstitial defect are shown by the non-ionic solids, whereas Schottky defect and Frenkel defect are shown by the ionic solids. Now we will learn these defects one by one. What is vacancy defect? See the figure here. What you find? That particles are present at the lattice site, which is shown by the dark circles. But few lattice sites are not having the constituent particles. When some of the lattice sites are vacant, the crystal is said to have vacancy defect. This defect can also develop when the substance is heated. Vacancy defect sometimes develop due on heating. So some of the lattice site will not be occupied by the constituent particles. What will be the impact of the vacancy defect? As the particles are missing from some lattice sites, so obviously the mass of the crystal will decrease, and because of that, density of the crystal will decrease. So because of the vacancy defect, there will be decrease in the density of the crystal. So this is the vacancy defect, which is shown by non-ionic solids. Second one is the interstitial defect. It is also shown by non-ionic solid. This type of defect is caused due to the presence of constituent particles in the normally vacant interstitial site in the crystal. That means all the lattice sites will be properly occupied by the constituent particle, and some additional particles will be present in the interstitial site or void, which is clear from the figure. Now, condition is the particle which is occupying the interstitial site must be very small in size so as to fit into this void. This is called interstitial defect, in which particles occupy the interstitial site or void. In ionic solid, what we find that point defect in ionic solid must always maintain electrical neutrality. That means if the number of positive ion and number of the negative ion in the crystal is same, both having the same valency, then such solid, ionic solid, will show point defect. Or total number of positive charge and negative charge in the ionic solid must be the same. This is the first and foremost criteria for any ionic solid to show the point. Now, what are the types of point defect in ionic solid? Ionic solid generally exhibit two types of point defect. One is Schottky defect and other is Frenkel defect. Schottky defect is identical to the vacancy defect. What is Schottky defect? In Schottky defect, equal number of positive ion and negative ion are missing from their lattice site. In the figure I am showing you, Let's see this figure clearly. One positive ion is missing from the lattice site, and likewise one negative ion is also missing. Count the total number of positive ions. All ions, cations and anions are univalent. So number of cation 1, 2, 3, 4, 5, 6, 7. And number of anions 1, 2, 3, 4, 5, 6 and 7. So number of positive ion and number of negative ion is same. So electrical neutrality is maintained. This is the Schottky defect, when equal number of positive ion and negative ion are missing from their lattice site. What is the condition for the Schottky defect? Schottky defect will be exhibited by the solids having high coordination number, and also in which the size of the cation and anion are almost equal. So if these two criteria are fulfilled, then such ionic crystal will show Schottky defect. What will be the consequences of this defect? Like vacancy defect, there is a decrease in the density of the crystal in Schottky defect. Why? It is clear from the figure that cation and anion are missing, so there will be less mass. And density is what? It is the ratio of masses to volume. That means mass is decreasing, so obviously our volume is the same, so the density will decrease. So Schottky defect is accompanied by decrease in the density of solids. Second, solid having this defect conduct electricity to a small extent. Why? Due to the presence of these holes, ions will be free to move from one hole to another hole, and thereby electricity will move in the reverse direction to the movement of the holes. So because of this, there will be some electrical conductance in the solid showing ionic, showing Schottky defect. Number 3, due to the presence of hole, what will happen? Lattice energy will decrease. Lattice energy is the product of the intermolecular force of attraction between the two oppositely charged ions divided by R square, the distance between them. So obviously the number of ions are less, so their lattice energy will be less, hence stability will be less and entropy will be more. So consequences of Schottky defect is that it is accompanied by the decrease in the density of the crystal. It will show some electrical conductance, and it will also show decrease in the lattice energy of the crystal and increase in the entropy. What are the examples? Examples of Schottky defect are ionic solids showing Schottky defect are NaCl, KCl, CSCl, KBr and AgBr. In NaCl, there are approximately 10 to the power 6 Schottky defect pairs per centimeter cube at room temperature. That is, there is one Schottky defect per 10 to power 6 ions. At room temperature, at 1 centimeter cube, there are 10 to power 22 ions containing 10 to power 6 Schottky pairs. So one Schottky pairs will be present in 10 to power 22 divided by 10 to power 6. That means 10 to power 16 ions. It is very well explained in the NCERT book. So please go through this portion properly and revise it number of times. Second one is the Frenkel defect. It is identical to the interstitial defect, but it is the combination of vacancy defect as well as interstitial defect. Why? See this figure clearly. This type of defect is created when an ion, a cation, when I write ion, you know well that cations are always smaller than the anions, and cation leave its normal lattice sites and shifts into the interstitial site. Get displaced into the interstitial site. So this type of defect is created when an ion, means cation, leaves its correct lattice site and occupies an interstitial site. Frenkel defect is the combination of vacancy defect and interstitial defect. In vacancy defect, what we find? We find that some of the lattice sites are unoccupied. Here also, this site is unoccupied. And in interstitial defect, what we find? That some of the extra particles are present in the interstitial site. Here you can see this is the normal lattice site which is not occupied by the cation, and the cation has shifted from here to interstitial site. So it is interstitial defect, it is vacancy defect. So Frenkel defect is the combination of Schottky defect as well as vacancy defect as well as interstitial defect. What are the compounds that shows Frenkel defect? Silver chloride, silver bromide, silver iodide, and zinc sulfide. There is one exception, silver bromide. It shows both Schottky as well as Frenkel defect. Now we will study what is the condition for Frenkel defect. Opposite to the Schottky defect, the coordination number of compound or a crystal, ionic crystal, should be low. In a Schottky defect, the condition was high coordination number. Here the low coordination number is the criteria. And second one, in Schottky defect, cation and anion are of comparable size. Here, large difference in the size of cation and anion. That means cation should be smaller than the anion. If these two criteria are fulfilled, then only the ionic solid is supposed to show Frenkel defect. What are the conditions? What are the consequences of Frenkel defect? Condition is very clear, that low coordination number and large difference in the size of cation and anion. This is the condition for a substance to show the Frenkel defect. What are the consequences now? As the particle does not leave the crystal, it only gets displaced from normal lattice site into the void. There is no change in the mass, hence the density of the ionic solid showing Frenkel defect remains undisturbed, unchanged. So, no effect on density of the solid. This is the first consequence. Second one, due to the presence of holes, it conducts electricity to a small extent. That means substance showing Frenkel defect also has electrical conductance to a small extent. And thirdly, what we see, that because of the shifting of cation from the normal lattice site into void, what we see, that two cation come closer. When the cation will come closer, what will happen? It will result in the increase in the dielectric constant of the crystal. So Frenkel defect causes increase in the dielectric constant. It does not affect the density, and it also causes some electrical conductance due to the presence of the vacancy. So this is all about the Frenkel defect. In board examination, this part is very important. And what is the question? The question is differentiate between the Schottky defect and Frenkel defect. So first point, what you will write in Schottky defect, The Schottky defect arises because of the missing of equal number of cations and anions from their normal lattice sites. Frenkel defect, on the other hand, arises due to the displacement or dislocation of constituent cation from their normal lattice site into a void. Number 2, in Schottky defect, density of the crystal decreases. In Frenkel defect, there is no change in the density of crystal. Third, in Schottky defect, substance shows some electrical conductance due to presence of hole. And in this case also, it shows some electrical conductance. Fourth, dielectric constant. In Frenkel defect, dielectric constant increases, but that is not the case in the Schottky defect. And fifth, Schottky defect causes decrease in the lattice energy. In Frenkel defect, lattice energy almost remains the same. However, there is slight change because of the disorder. Entropy increases slightly, and in Schottky defect, entropy changes large due to missing of equal number of cations and anions. So, there will be a numerical problem given in the NCERT book in exercise on Schottky defect. Please solve it out and read this part very carefully. In my next video, I will explain you about the non-stoichiometric point defect and metal deficiency defect, their consequences, condition for the substance to show these defects. Thank you.